Welcome to today's webinar. We will discuss biocatalysis as an effective, economic, and ecological sound approach to boost biogas generation. My name is Matthew Christman, the Executive Director of the Wisconsin Biogas Council. The Wisconsin Biogas Council's mission is to advance the biogas economy of Wisconsin through collaboration, education, and research to achieve sustainable communities, environmental improvement, and energy independence. Today, it is my pleasure to introduce Drylet, an innovative company that is focused on accelerating nature's biological remediation process through the use of its proprietary biocatalysis. As you will hear today, its award-winning technology combines material science and microbiology to harness the power of nature and deliver consistent, beneficial results with regard to organic waste management and, as you're about to discover, biogas generation. Our presenter today is Malcolm Fabi, Chief Operations Officer at Drylet. He earned his Ph.D. in chemical engineering at the University of Cambridge in England. He has authored over 50 journal and conference papers and holds several patents for commercialized wastewater technologies. Malcolm also holds an MBA from the University of Chicago Booth School of Business. Prior to joining Drylet, Malcolm's career spanned more than 20 years in corporate research and the development and management of environmental technology solutions. In particular, he served as the Global Market Director at Praxair Incorporated, a Fortune 500 company, then as President of Hydrogel USA, the environmental software solutions provider that developed the world's premier wastewater treatment plant simulation and optimization application, GPSX. After Malcolm's presentation concludes, we will take time for a Q&A session, so please ensure you share your questions as they come by, clicking on the Q&A button in the toolbar at the bottom of your screen. And now to you, Malcolm.
Thank you so much for that introduction. I want to welcome everyone who is taking part in today's webinar. Thanks for taking the time. Today's conversation will be broken up into 5 parts. I'll start by providing an overview of bioaugmentation, and I'll talk about the fundamental principles that underlie bioaugmentation. We'll then talk about the basics of anaerobic digestion, and we will then jointly evaluate methods that are typically used to enhance anaerobic digestion, and then discuss the particular ways in which biocatalysis can actually help us do that. We'll round out with conclusions, and as was indicated earlier, we'll be able to take some questions and have some open conversations about how this potentially could be of use in some of the operations that you have. The biological remediation of waste is fundamentally the most widely utilized approach for dealing with organic contaminants. And whether we're talking about wastewater treatment or whether we're talking about digesters, fundamentally, we're starting with a carbon-based waste. So if you think about, a typical feedstock going into a farm-based digester, it would essentially comprise of undigested foods that are coming from the intestines of an animal. It will comprise of bacterial cells that are within the gut. It will also comprise of things like straw, like bedding, like feedstock, materials that have been provided that have not been degraded. What will be common to all those materials is that they are carbon-based. And so all of the carbon-based material that goes into a biologically remediated process relies on microbes to be degraded. In the context of anaerobic digestion, we take the carbon-based waste, we expose it to microbes, and in the absence of oxygen, which is what we have in an anaerobic digester, roughly 30 to 60% of the organic material that is provided is converted into a gas. So for every 100 pounds of, let's say, feedstock that is provided to a digester, about 30 to 60 pounds equivalent of that will be converted to biogas. There will be another 5 to 10% that would typically be converted into new cells. So as the bacterial cells feed on the organic waste, they will also generate some new cells. And then finally, there will be somewhere between 30 to 65% of the feedstock that will remain undigested. And so one of the unique challenges that we have in anaerobic digestion is that our best performing digesters often do less than about a 50% conversion of the volatiles. What that means is that even after these digesters are finished doing all that they can do, there's potentially up to 50% or more of the organic material that we fed to it that can still be converted into incremental biogas. The more biogas we can generate in the digester, the more methane we capture, the less would be the possibility that we would have fugitive emissions of methane from that undigested material that is still retained within the digestate. So fundamentally, what we focused on in Drylet is asking ourselves the question, are there ways in which we can actually intensify bioremediation? We know we can improve bioremediation, and part of the reason why we know we can do that is we know there are feedstock like fat oils and grease, where the conversion rates are not just 30 to 60%, the conversion rates in many cases are between 70, 80 to 90%. So if we can find a way to make that feedstock more available to the microbes, then we know that we can actually have higher levels of conversion. So our mission at Drylet has been to just fundamentally find ways of intensifying bioremediation and doing that in a way that ensures that we still have reliable and robust treatment while also getting benefits like enhanced biogas generation. And the need for such solutions is immense. So if we think about the entire gamut, the entire scope, the entire field of sectors that require solutions to the significant amount of solids that they have to deal with. I mean, we're talking about almost 40 billion gallons of wastewater being treated daily, generating roughly 65 billion pounds of sludge. And if we look at the livestock side, there's over 6 trillion gallons of manure, both from swine and from cattle, that are generated on an annual basis. So finding ways in which we can do more with those solids, in which we can break down more of those solids, in which we can make our digesters more efficient and effective, would be extremely significant, not just in helping us generate more biogas, but in also providing us with options for mitigating, reducing, and better handling the significant amounts of solids that are being generated through all these different processes. If we look at a typical microbial system, there are 8 factors that determine the type of microbes we have. Those factors are the food, which in the context of a farm-based digester, we might really have no control over, because the food that we get is essentially the waste coming from the animals. If we think about one place where we could have control over the food, it might be in a brewery, for instance, where we can actually go buy hops, we can determine exactly what we want to put into the digester and have remarkable control over the food going to the digester. But in most of the applications I'll be talking about today, we're basically dealing with waste, whether it's biosolids from wastewater, whether it's feedstock from digesters, or whether it's mixed waste systems that are taking part feedstock from animal production and are going out and taking things like fat oils and greases that are then being fed to that digester. But those factors, again, include the food, the temperature of the system, the hydraulic retention time, and the sludge age, which in many digesters, if they are well mixed, might be the same. So in a well-mixed digester, both the liquid and the solid streams spend exactly the same amount of time in the system. But as all of us on the call know who have experience with digesters, there might be situations where your sludge age and your hydraulic retention time might be different because the mixing is not as efficient and you might have partitioning, a separation of phases. So we'll talk about later on in this presentation, examples of some of those types of digesters where the hydraulic and the retention time and the sludge age might be different. And then other factors like having the right amount of nutrients, the pH and alkalinity. All these 8 factors impact the type of microbes we have. And one of the things you will immediately recognize is that any attempt that we're making to try to improve, change, alter, or modify the microbial consortia tends to require costs or significant amounts of energy. So for example, we know we can improve the operations of a digester by increasing temperature, but increasing temperature means we have to buy heat exchange systems, we have to burn some of the biogas or bring in natural gas to burn to provide us with that energy. If we want to increase the sludge age or the hydraulic retention time, it means we have to make those digesters even bigger. And as we know, most well-mixed digesters tend to be somewhere within the 15 to about 30-day hydraulic retention time and sludge age time frame. But one way we can change the structure of the microbiology in the digester is actually to extend the sludge age and hydraulic retention time by building bigger or deeper systems. Nutrients can be another way to impact what's going on in a digester. And then obviously the pH and the alkalinity, there are different ways in which those can be modified as well. But the critical thing is that all of these are going to require some type of capex in order, to be able to implement, whether it's in pumping systems, whether it's in building additional basin capacity, whether it's in buying heat exchangers, whether it's in having engines that can allow us to burn gas and capture some of that heat and transfer and translate that into the digesters. So what we fundamentally do with biocatalysis is to take a step back and ask ourselves the question, are there ways in which we can actually use microbes to achieve these outcomes we're looking for? If we know the type of microbes that we want to have, are there ways in which we can go into nature, find those microbes, and then deal with the challenges of making those microbes viable by putting them into a system where they did not naturally emerge, but systems in which their presence could actually potentially improve what's going on. That entire process of improving what is going on in a microbiological system, like an anaerobic digester, is called bioremediation. There are different types of bioremediation, but what we'll focus on today is a particular type of bioremediation that is referred to as bioaugmentation. So we will be talking significantly today about bioaugmentation, and Drylet's particular focus is on cellular bioaugmentation. This is taking materials that are found in nature, microbes that are found in nature that are not modified in any way, and then presenting those microbes on platforms, unique platforms that we'll talk about as we go forward in this discussion, into a biological system like an anaerobic digester, and ensuring that those microbes are viable and that they provide us with the outcomes that we're looking to have in the system. In principle, a wide variety of microbes can be bio-augmented. So for instance, in a digester, we have fermenting microbes that basically take the waste that we put in and break them down and convert them into volatile fatty acids, which is an extremely important step in the digestion process. We have methanogens, which are a unique set of microbes that are able to take volatile fatty acids, hydrogen and CO2, and convert them to methane. We have lipophiles, which is a class of organisms that are laser focused on being able to break down fats, oils, and greases. So just a wide variety of different types of organisms that we could, in principle, load onto a platform and introduce into a biological system. Now, if we take microbes that might not be native to a biological system and we introduce them into that system, there are three fundamental challenges that we have to overcome. The first challenge is, how do these microbes get access to food? So I'll give you a few examples. In a typical digester that is generating about 250,000 cubic feet of gas a day, that digester might be fed with hundreds of thousands of pounds of solid material. we would typically be dosing into that digester no more than about 10 to 20 pounds of microbes on this platform on a daily basis. So how do we enable a very small amount of microbes that are going into a system with significant quantities of other bacterial cells? How do they even get access to food? So when you take the dosage, and as we will talk about this in subsequent slides, a typical digester that is dosed with the Drylet Biocatalyst might have about 10 to 20 parts per million of material. When you have a digester that has 2% solids, 2% solids is basically 20,000 parts per million. Many of our digesters have as much as 5%, in some cases 7% solids. A 7% solids digester is 70,000 parts per million. So how do we take 10 parts per million of microbes that we're dosing into the system and have those types of microbes compete with 70,000, 20,000, or 50,000 parts per million of other microbes in the system? How do they get access to food? The second one is viability. Every microbial ecosystem has its own unique viruses. It has its own unique higher order organisms. So the viruses are smaller than bacterial cells. The higher order organisms are larger than bacterial cells. Every natural microbial ecosystem has those. So if we take this very small amount of bio-augmented material and we put it into a digester, even if they get access to food, how do they survive the unique viruses that are present in the system? If we're in a swine-based system, there are porcine viruses that are unique to pigs. If we are taking these bio-augmented microbes into a cattle or dairy-based system, there are bovine viruses that are unique to those animals. How do we make sure that these microbes are actually able to survive those types of situations? And then the final one is retention. If we're only dosing small amounts of microbes, one, because that's all that we need, and secondly, because it is cost prohibitive to be dosing significant levels of microbes, how then do we ensure that they are retained within the system? In Drylet, we have addressed these problems by coming up with a unique solution. And that solution is to take the targeted microbes that have the properties we're interested in and to load them onto an engineered porous media. So the picture you're seeing in the middle is what that loaded media looks like. So the red circles, inside the red circles, you see some spherical, spiky materials. Those are actually bacterial cells. You can see void spaces in here. Those are that's the porous interior structure of the media that we use. Each pound of this media material has 700,000 square feet of surface area. We will see later that that is equivalent to about 150 basketball courts. And what that allows us to have is a significant amount of surface area, which is important for absorbing food. So even though we're dosing a small amount of material, the high absorptive capacity of the media itself allows food to be pulled into the media, and that food then becomes available to the microbes. So the microbes don't have to compete with other microbes. We're using the material science properties of the media to provide these microbes with a leg up, to provide them with an advantage in terms of the absorption of the food into the system. The second thing we know is that when microbes form a biofilm, they are extremely resilient. One of the most resilient biofilm systems we have is in our mouth. Every day, in the morning and at night, we brush our teeth. And all we're trying to do when we brush our teeth is to try to remove those microbes that are in our mouths that might cause, mouth odors, or that might produce acidic material during the digestion process that's taking place in the mouth that can lead to, basically lead to cavities. But we also know that we have failed in eliminating those microbes because the very next day we have to repeat that process. A biofilm is extremely resilient. And what these microbes form, as you can see here, is they attach to the interior surfaces within the media, and they form a biofilm. And that allows them to be able to withstand viruses, to be able to withstand toxins. It allows them to be robust and to be able to adapt without being eliminated within whatever system you put them into. The final one is retention. A typical microbial cell is about 0.4 to 1 micron in size. It has the same specific gravity as water. If I dose microbes into a typical microbial ecosystem, those microbes will be retained for the hydraulic retention time. What we do, however, is we load these microbes inside a media that is 200 to 600 microns in size. What that allows us to do is, if the system is well mixed, the particles stay within the mixed system. If the system is not well mixed, then the particles settle into the sludge layer, which is where the volatile solids we're trying to destroy actually is. And if we have a separation between the hydraulic retention time and the solids retention time, the solids retention time tends to be way longer than the hydraulic retention time, which means we are actually able to retain these particles for longer, reducing the need to have significant amounts of supplemental dosage, reducing the overall cost, and ensuring that we can have reliable and predictable outcomes as we move across systems. So in essence, what we do, we take microbes, we load them on a food grade substrate material, we form products that are 200 to 600 microns in size. The product itself is a dry flowing a dry powder. It's a free flowing material that can be easily and readily dosed. It can be dosed into the feed. It can be dosed directly into the digester if we have access. And in essence, we have a platform that allows us to protect the microbes and deliver them reliably into any system that we're trying to remediate. So bringing all of that together, a pound of the material, as I said, has 700,000 square feet of surface area, which is equivalent to 154 basketball courts. And by loading the microbes into this media, we're able to enhance the viability. We provide an increased surface area, improved physical chemical properties. We're able to ensure that the microbes are not killed off by things smaller than them, like viruses, or eaten by things bigger than them, like higher order organisms. And then finally, we're also able to ensure that because of the size of the media particles, that we're able to retain the microbes in the system for systems that might have poor mixing, where you have very distinct liquid and solid phases. And if the system is well mixed, then the microbes, the particles and the microbes are able to be well mixed within the system and retained within the system as well. Using this technology, we have a variety of applications, both on the wastewater side and on the digestion side. And what we'll be focused on today is the work that we do in helping to boost anaerobic digestion. We also do a significant amount of work on the livestock side. So our technology has been applied for things like mitigating foam formation in swine farms, reducing the amount of solids accumulated in manure systems and lagoons, and helping to improve the overall outcomes in terms of livestock management. Today, we'll talk about a number of case studies that address both manure-based, both farm-based digesters, as well as some relevant examples from municipal and industrial digesters as well. As a company, Drylet's experience spans a number of different sectors, but as I indicated, our focus today would mostly be on the work that we do on the anaerobic digestion and the waste to energy side. We're now going to take a more detailed look at anaerobic digestion. If we look at the anaerobic digestion process, there are 4 distinct steps. The first step is the hydrolysis step. And what happens in the hydrolysis step is we're taking solids, whether these solids are bedding materials, whether these solids are fat stores and grease that are being brought in a mixed waste type system, or whether these are undigested materials that are coming from the guts of the animal, or whether they are bacterial cells that are being pushed out from the gut of the animal itself. The manure, that is the poop from cows or swine, contains about 50% bacterial cells. Those bacterial cells are coming from the gut of the animal. Nothing can eat something that's bigger than itself. So when we're faced with a steak, the first thing we do is we take out the knives and we cut that steak down into manageable pieces. Pieces that are no bigger than the size of our mouths. Is the same thing for bacterial cells. A bacterial cell can only feed on material that is soluble, material that is small enough to go across its cell membrane. And if we consider the fact that a bacterial cell is about 0.45 to 1 micron in size, then it means we have to take these big chunks of material, straw, embedding, fibrous material. We have to take all these bacterial cells that are being pushed out into the manure, and they have to be broken down into their small pieces, into molecules, into compounds. That is the most difficult process in anaerobic digestion. The hydrolysis step tends to be the rate limiting step in most digesters. Taking those big chunks, whether they are big chunks in terms of size or whether they are big chunks in terms of the complexity of the molecules, and breaking them down. The next step is acidogenesis and acetogenesis. Combined, steps 2 and 3 are called the fermentation steps. And what happens in those fermentation steps is we take the big molecules that come out from the hydrolysis process and we convert them into volatile fatty acids, hydrogen, and CO2. And then the final phase is methanogenesis, where we take the product of the fermentation steps and a unique set of microbes, the only microbes that are known to be able to do this, take those byproducts and convert them into biogas. If we were to improve each of these steps using bioaugmentation, what you see to the right of the slide are the actual steps we would need to take. So if we're trying to improve hydrolysis, which we know is the rate limiting step, and we know that's the case because, again, as I indicated earlier, our best performing digesters would do about a 50% reduction of volatile solids. What that means is that a big chunk of all of that solid material, all of that food that's coming in, is not broken down, is not going through the hydrolysis step. How do we address that? Well, one way we could do it is we can boost the amount of hydrolytic enzymes that are being generated. We can enhance the breakdown of the cells. We can enhance the cleavage and the breakdown of those large molecules. If we were trying to improve the methanogenesis stage, well, we could go find methanogens. We can take those methanogens and we can introduce them into the process. So what you find here are the very distinct steps from a bioaugmentation perspective that we can take at each step. If we take a closer look at hydrolysis, we begin to get a sense for why hydrolysis is extremely difficult. There are typically two types of solids going into a digester. On the one hand, you have those materials that have long chain molecules. So every food eventually breaks down into being either a carbohydrate, a fat, a protein, or maybe in the context of things like straw, lignin material, right? The challenge we have with those long chain molecules is we need to break them down. We need to cleave them. And why do we need to do that? We need to get them small enough that they can actually pass through the walls of a bacterial cell. Because without passing through the walls of a bacterial cell, the bacterial cell can't feed on them. That's the fundamental challenge, is taking those long chain molecules and breaking them down. The challenge with biological cells and plant cells is even more challenging. So if you take a bacterial cell, for example, as I indicated, 50% of the solids in manure, the poop coming straight out of the cow, is bacterial cells. The challenge we have there is that there are carbohydrates, there are proteins, there are fats, but they are all encased inside the cell wall. So before we can even access the food to start breaking it down, we have the task of breaking that cell wall. we have to lyse the cell before we can even access the food and start cleaving it up and breaking it down. It's the same thing with plant cell tissue. So if you look at a typical, if you look at bedding material, if you look at fiber, if you look at straw that the animals are feeding on, if that for any reason ends up in the feedstock, well, before we can actually access the cellulose to break it down, we have to deal with this cell wall. And the cell wall has been designed by nature, whether it is a cell wall of a bacterial cell or it's a cell wall of a plant, to be extremely resilient and challenging to break down. That's why these organisms thrive in the first place. That's why this is the rate limiting step. So two fundamentally different types of solids. The easier ones to deal with are the ones where all we're dealing with is the chemical compounds themselves. The more challenging ones is where we cannot get to the chemical compounds without breaking up a cell wall or splitting up a plant cell wall and making the materials that it contains available for hydrolysis. So oftentimes, when we say something has a 50% volatile sludge reduction, what we're really saying is that the primary solid fraction, the fraction that is just breaking up the long chain molecules, we typically have as much as 60 to 80% volatile solids reduction of that fraction. The more difficult to reach fraction is where we have bacterial cell walls or plant cell walls. And oftentimes we have less than about 40% of that fraction of the solids actually being degraded. If we were to improve the hydrolysis of this hard to degrade fraction, then what we're looking for are ways that we can enhance cell lysis, rupture the cells, and promote the release of the cells. Well, there are different ways we could do that. So we can take a bacterial cell, for example, and we can just mash it up. We can subject it to pressure, we can subject it to temperature, we can increase the temperature, we can stress that cell. We know that anytime we stress a cell enough, we can rip it apart and we can release its cellular content. The same thing for plant cells. We can take that lignocellulosic material, that fiber, and we can mash it up, we can subject it to heat, we can subject it to harsh chemicals, all in an attempt to break down that cell wall. The challenge with that is, even though these techniques work, these techniques will also affect other classes of microbes in the system. So not only will they make the food more available, but they will also affect the microbes that do hydrolysis, they will affect the microbes that do fermentation, and they will affect our methanogens, because all of these microbes are highly sensitive. Anything that improves cell lysis is also going to affect all of these microbes that we want to, whose health we want to retain in the system. So what we often need in that situation is we would need an approach that can be provided in situ and that does non-destructive lysis. So there are, for those on the call who have experience with this, technologies like thermal hydrolysis, like pressure homogenization, like chemical hydrolysis and ultrasound that can be applied as pre-treatment steps. They are typically never attached to the digester because they are indiscriminate technologies that can affect all cells. But oftentimes what these technologies are used to do is to make the food more available, is to break down the solids, is to lyse the cells. Our approach in Drylet is to say, are there ways in which we can actually do this, get the same types of outcomes, but just leverage microbes? Because microbes are extremely effective. And if we can find the right microbes and ensure that they can survive within the context of a digester, then we can have a chance at being able to deliver these solutions in a way that can be targeted and that can be coupled directly to the digester, and that does not require significant amounts of capex, and in our case, does not require any capex at all. The approach we take is threefold. So one is our solutions are always data-driven. We're typically starting with the operational data about the digester. We're looking at the things like the solids retention time. We're looking at the specific gas generation in the digester, which is the cubic feet of gas generated per pound of volatile solids removed. We're looking at factors like the amount of volatile solids destruction that is currently being achieved in the digester. In some cases, in a very few number of cases, we might even look at the microbial landscape. So if we look at the data and there's indication that there might be things like maybe and inhibition of methanogens. You know, we might do a more detailed look into that, but 95% of the digesters we look at, we typically don't need to do that because the issues with the digesters are clear. It's normally a limitation in hydrolysis. And then the final one is we then determine how much biocatalyst we need. And we determine that just simply based on how much more incremental gas are we trying to get. We typically dose a pound of our material for every 5,000 cubic feet of incremental gas. So if we went into a system and we wanted to increase gas generation by 10,000 cubic feet a day, that would be 2 pounds of a biocatalyst being dosed into that digester on a daily basis. We've worked across every conceivable type of digestion process. So starting with plug flow systems, which are very common in Wisconsin with the DVO style systems, to partial mixed lagoon systems, not so common in Wisconsin, probably because of the temperature limitations that many of these systems have, but very common in the warmer parts of the country, very common in California, quite common, interestingly, in places like Missouri, very common in Texas. And these are basically just holes in the ground, lucky if we have any mixing. But what you see is that in these systems, you actually have a 4-phase system. 4 phases in the sense that you have a scum layer, crud. So fats and oils have a lower specific gravity than water. So any fats, oils in the system, that tends to float right away to the surface. And it thickens and hardens over time. These systems can be, in many cases, 5 to 6 feet deep, this particular layer. You have the liquid layer, and then you have the solids layer at the bottom. And this solids layer would comprise both of settled material that has accumulated over time, as well as heavier, fresh material that is coming in the influent. So the particular challenges that you have in a partial mix system is ensuring that you have a product that is able to address both the sludge layer that is at the bottom, a crust that is at the top, as well as a significant liquid layer that also still contains the digestate and material that you still want to degrade. And then we have complete mix systems, which are very common on the municipal wastewater side. This is a picture of what our technology is able to do. So all the technologies you see put up here, these technologies would typically require significant capital expense. In the case of thermal hydrolysis, for example, all we're doing in thermal hydrolysis is we're taking those cells that we want to rupture. We subject them to temperatures that are higher than the boiling point of water. Why do we do that? We know those cells, whether they're bacterial or plant-based, typically those cells would have about 90 to 95% water. So if we can heat up those cells to temperatures that are higher than the boiling point of water, we can actually make them explode from the inside out. Then in thermal hydrolysis, we raise the pressure. We raise the pressure to anywhere between 10 to 15, in some cases to 30 times atmospheric pressure. What does that do? It allows us to collapse those cells on themselves. As you would imagine, we need specialized equipment, we need temperature, we need heat, we need capex. Pressure homogenization does the same thing. It increases the pressure to, in many cases, almost 2,000 times atmospheric pressure. But the goal there, the goal of all these systems is to stress the cell and rip that cell open. They can be quite expensive. What you're seeing in the far right here is actually our technology being dosed into a digester. In this case, this is a municipal digester, and what you're seeing in the picture on the top is the material being dosed into the thickened sludge overflow. So in this particular plant, they have a thickened sludge overflow, and we're dosing the material into that thickened sludge as it makes its way into the digester. We've worked across a variety of digestion systems, both municipal plants, industrial facilities like rendering plants that are dealing with different types of high strength wastes, as well as dairy, cattle, swine, and we'll go into a few specific examples. So in this particular example, it's a 55 million gallon a day plant. It's a sewage facility, and they generate about 1 million cubic feet of gas a day. We dosed about 50 pounds of the material daily into this system, and they were able to get an increment of about 300,000 cubic feet a day of gas. That is about 60,000 cubic feet for every pound of product that was dosed into the system. We typically begin seeing results within about one sludge age. So in this case, this plant had a 20-day solid retention time, well mixed, completely mixed digester, and they were able to start seeing results within about a 20-day time frame. So we normally expect to start seeing results within about within about one sludge age, which in this case was about a 20-day time frame. So within 1 to 2 sludge ages, we expect to begin to see results in the system. This might be closer to home. So this is a Wisconsin-based digester. At the time we did this work, this particular facility was actually generating power on site. They were generating about 250,000 cubic feet of gas a day. We dosed product, about 16 pounds of material into this digester. And they went from about 250,000 cubic feet of gas a day within about a 15 to 30-day time frame. That number had increased about 33% to close to 340,000 cubic feet of gas a day. So they got an increment of 80,000 cubic feet of gas a day by dosing the equivalent of 16 pounds a day of material. So a pound of material basically giving them close to about 5,000 incremental cubic feet of gas. We started observing results here within about a 15 to 20-day time frame. This particular digester had a 15-day solids retention time. This third example is from an industrial facility. It's a rendering plant. So highly concentrated waste, but most of it liquid, in the liquid phase, coming into this covered partial mix digester. This is the one that I'm highlighting here in the middle. The facility had 2 challenges. So one was very low levels of gas generation, but it was also clear that the facility there were inhibitions. So the pHs were remarkably low. The specific gas generation rates were also very low. The volatile fatty acids were high. And what that immediately told us was that methanogenesis was inhibited. So in this particular case, we had to do 2 things. One was provide product to enhance hydrolysis, but also to provide bioremediation for the methanogens in the system. And this plant went from an average generation of 500,000 cubic feet of gas a week to now generating well over 2 million cubic feet of gas a week. And then another partial mix system. This is now dairy-based. This is out in California. Another partial mix type system, dairy farm with about 1,500 cows. And in this case, they were able to dose enough product to give them about a 15% boost in gas generation. So very quickly, I'll walk through a few things of interest. One major question would be, if we increased gas generation, does an increase in gas translate into an increase in the energy content of the gas? The answer is yes. So this is the example of the plant where we were generating about 1 million. We went from about 1 million cubic feet of gas a day to an increase of over 30%. In that particular plant, they were generating power using biogas. And what you can see here is in this first portion, the first two charts here, is they went from 657 megawatt hours per month from biogas to generating 869 megawatt hours per month from biogas. As you might recall, that plant also generated energy from a number of other sources. The increase in gas, roughly about 35%. The increase in energy is within the same range as well. So yes, an increase in gas would translate into a similar level of increase in the energy content. And as you might imagine, when you actually look at the gas composition, the blue represents the pre-Drylet period, the red represents the period with the use of our product. You can see that both in terms of the methane content as well as the carbon dioxide content, that the composition of the biogas essentially isn't changing. One of the things we typically observe, this is not something we see all the time, but we observe this in a number of our applications, is that the H2S levels also tend to reduce as well. We have applied our technology across a broad range of systems. So we've worked with complete mix, plug flow, partial mix type digesters. We've worked with a variety of different types of substrates, from single substrates, from biosolids on the wastewater side to dairy systems where the fundamental feed 100% is from the dairy operations, to systems where we have mixed waste, where the dairy or the livestock-based manure is only 10-20%, and those farms are bringing in other materials and they're using those other materials to actually subsidize for the cost of operating the digesters. We typically do that not in places like Wisconsin. We see quite a bit of that in places like Massachusetts and Connecticut, where the subsidies and the incentive structures are different, and where the incentive really is about green energy, and that's what the farms are incentivized to actually focus on. In terms of costs, different types of gas from different feedstocks have different values in different programs. So whether you're talking about the RFS program with the EPA, whether you're talking about the LCFS program, there's a range of value for the gas that is being generated. And what we've done here is the slide on the left is one we've borrowed from Blue Source that just shows the different levels of value that you can get for different programs, depending on things like your RIN designations, as well as the CI scores and the credits associated with your system and your program. And we've compared that to what it would typically cost to generate 1 MMBTU unit with the use of the Drylet biocatalyst. And what you can see here is that it would typically cost somewhere in the region of $6 per MMBTU to generate an incremental unit of MMBTUs by adding a biocatalyst. And that compares favorably well to the potential value that you can get if you had a digester that was perhaps part of an RFS and LCFS program. This next slide gives you a sense for the mechanism. So we dose a pound of material. That pound of material breaks down an incremental, 500 pounds of solids. We know that you're generating about 10 to 15 cubic feet of gas for every pound of solids you reduce. So a pound of material immediately translates into about 5,000 to 7,500 cubic feet of incremental biogas. And as we've indicated, when you look at that in the context of the cost of the biocatalyst itself and the incremental gas it is generating, you work it out that you're looking typically at somewhere in the region of $6 and less per MMBTU of incremental gas that is being generated. The critical thing, very important to note, there is no capex. There's no pump, there's no pipe, there's nothing that changes in the system. All you're doing is you're dosing this biocatalyst into the process. How do we work? Everything we do is data-driven. We're starting with facility data. We take that data, analyze it. It allows us to come up with a model of the plant, allows us to understand what's going on in the plant. And in many cases, we then do a risk-free demonstration. We're able to determine the increment that the plant can get and the potential economic value of that. And that allows us to work with the operator to demonstrate the value of the product in a way that doesn't put them at technical or economic risk. And then we typically would move forward to some type of business approach. To summarize, we have demonstrated over the last few years that biocatalytic augmentation can be a viable, robust, reliable, replicable way of enhancing biogas generation. As long as a system has less than 60% volatile solids reduction, which is almost 100% of livestock-based digesters, then we believe that there's actually an enhancement that can be provided by bioremediation. The benefits are reduced operating expenses, an enhancement to revenue-generating units like biogas, and then for somebody that has built a system where they expected maybe a 50% volatile sludge reduction or less, by doing nothing more, by investing in no more capital expense, you can actually get more out of that system. One of the things, obviously, that we need to consider is if your digesters are In the RFS or the LCFS program, we need to consider what the implications are of increased gas generation with regards to the overall, CI scores and other units of performance and value relevant to the program. The approach can be applied to any type of digester. And again, it bears emphasizing that it's a zero CAPEX solution that it allows us to do more with our existing assets. Thank you, and I believe we have just a little bit of time for some questions.
Well, good afternoon, everyone. So if you have questions, you have a couple of options. Either you can use the Q&A button that's at the bottom of your screen, or you can raise your hand and we can actually let you speak via audio. And perhaps I'll ask the first question. Let's see. Let's ask what does the typical product application process look like? Is it mostly done by hand, or is there mechanical automated methods that you can utilize in systems? There's less or different opportunities for that.
Yeah, so it's typically done by hand because the quantities we're dosing tend to be quite small. So for most operations, we found that they've just had a preference for doing this by hand. As I indicated earlier, for the Dalman East facility where we were able to get an increment of about 80,000 cubic feet of gas a day, they were dosing 16 pounds of material on a daily basis, and they just found it more convenient to just dose that into the feed that was going into the system. We do have automated delivery options, but in many instances, it's actually a hand dose, manual dosage is what most people opt for.
While we're waiting, let's see. We have another question about how do fluctuations in the volume of feedstocks impact the process?
So the fluctuations don't typically have any major impact on the process. One thing for us to remember is anything we dose into a digester, at a minimum, tends to spend the hydraulic retention time or the sludge or the solid retention time in the digester. So a typical digester, for example, would have about a 20-day retention time. So, small day-to-day fluctuations are not that significant because whatever you dose in is going to be there for, on average, about 20 days before it comes back out the other end. Averages, as long as we have a good sense of what the average is, and normally we can actually pick that from what's going on the biogas generation side, that's more than sufficient. So when we determine what we're dosing to a digester, we make that determination based on the average amount of gas being generated. And as I indicated earlier, the goal being that every pound of material we're dosing is helping us get an increment of about 5,000 cubic feet of gas.
Okay. I think a good next question would be, if you're doing work with farm-based digesters, is there any impact on the leftover solids as far as their use as a bedding material?
Well, so this is what's interesting, right? Is relative to when we started, you might have less bedding because your bedding material is food. So there might be some reduction in bedding material. So for example, if we're generating 80,000 more cubic feet of gas a day, and we know that there's about 10 cubic feet of gas per pound of volatile solids being destroyed, it means we just eliminated an increment of somewhere between 6,000 to 8,000 pounds of solids. That material is coming from solids that have, been trapped or embedded within the digester, but it's also from the bedding material. So yes, there could be some reduction to your bedding material because that's food, that's volatile material that we're then just converting into biogas.
Okay, and I guess another question would be, what are the longer term environmental impacts once the polymer and the biocatalyst has passed through the system?
No long-term environmental impacts, for two reasons. So the first is we're dealing with so the media itself is silica oxide based media. It's essentially sand. It's just engineered sand. So extremely benign. It's a food grade material. It doesn't have any deleterious impact on the environment. And then more importantly, we're dosing remarkably small amounts of the material. And as I indicated earlier, we're typically dosing about 10 parts per million. So in the matrix of solids that are going out, less than 10 parts per million of that material is going to be this silica-based media that we're dosing into the system. So benign material, environmentally friendly, food grade. And in fact, that silica material is already in all of the foods we eat. So if you're using salts, you're using condiments of any kind, roughly 1 to 2% of all of those materials would have silica in them. That's what prevents them from clumping. So extremely environmentally friendly material.
Okay. I guess one other would be, have you done any projects that are associated with wastewater treatment as the leachate from landfill operations? And is that something that you can apply the technology for processing those organics, or is there too much toxic components in that mix to be considered for this application?
So we haven't treated leachate directly, but we have treated wastewater plants that receive leachate and have had process upsets because of the leachate they treat. So we've been able to help them stabilize. So yes, this material can actually be applied for the treatment of leachate. I didn't go into it in detail, but if you recall, there was a portion where we talked about 4 different market segments. There is a market segment we deal with that is actually industrial, toxic materials. So high strength materials like oil spills, chemical spills, recalcitrant material that we have a product line that we typically address with that. So it's a different microbial consortia, but it's the same platform principle that is utilized for the product that we use on the anaerobic digestion side.
Okay, as I think we have time for one more question. So we'll give it 1 second to see if there's anything posted. And right now there isn't. So I will ask if your process was applied to a digester that was focused purely on food waste. Is there specific practices that need to be undertaken compared to if the digester was more geared towards dairy operations or some other application? Or is it more feasible to use it in that situation because it's more food?
I think that's a great question. So what we found is useful. So for many digesters that have food waste, one of the fundamental challenges they have, there are 2 challenges they have. One is food waste is an extremely concentrated material. And for some people that deal with food waste, they tend to find some instabilities every now and again when the food waste gets dosed for 2 reasons. One is when food waste breaks down, it's breaking down into volatile fatty acids. And if you're forming those volatile fatty acids too quickly, one of the things that begins to happen is, you may have situations where you're changing the structure of the digester, where you're generating volatile fatty acids so quickly that it's affecting pH, it's affecting the surface tension within the digester. It might lead to things like foaming. It might lead to inhibition of your methanogens. One of the things we found to be useful is to actually pre-dose the product into your food waste holding tank. So we have a number of clients who actually do that. They have digesters where about 10% of it is the livestock waste, and then they're bringing in about 50 to 80% of the feedstock is food waste. And if they used to have process upsets, well, what we found works best for them is in whatever holding tank you have, dose this material in. You want to start breaking down that food waste. You don't want it to get into your digester as a chunk that then floats up to the surface and becomes and starts forming a crust at the top. You want to make sure that you begin to break those long chain molecules, that the lipophiles that we have in the product begin to help you break up those chunks, so that when you go into the digester, it's an eased out process. That's the only difference we would normally recommend. Is if you have food waste, dose the product up front. All of the types of feedstock, we just recommend that you dose them directly into the digester. By dosing up front, you can get some work going before the actual dose into the digester with food waste.
Okay. Well, thank you very much, Malcolm, for presenting today, and thank you everyone for attending. The presentation has been recorded, so we will get that out to everyone and make it available in the next news announcement. So thank you again, everyone, and we look forward to speaking with you again in the future.
Thank you. Thanks, everybody.